We've reached a big question. Is Node.js multi-threaded? Chances are you're well aware that computers with more processors and processor cores are more powerful, more expensive, and generally more desirable. And the way that we take advantage of our multiple cores to run our programs faster is by using threads. But what exactly are threads? And how do they help us? Let's look back at our node diagram. What we have here is a series of internal components of the Node.js process, and how a function call like fs.open might flow through these internal components. Well, the Node.js process, like any process on your computer, represents a program being currently executed. In this case, the Node.js executable. I want to show you a diagram that will help put things together from how exactly the Node process runs on your operating system to how your CPU allows you to run code asynchronously. We start from processes. What happens when you run a process on your machine? Anything like the Chrome browser or the Node process. Well, processes are containers containing your code, which lives in the memory of that process. So we might have some code with a few functions, like a first function that calls this second function, and the second function just returns the number 42. And then below, we have this code which creates a new thread using the code from that first function, and then creates another thread using that same function. Now, this is pseudocode. It's not code in any real programming language, but it's a lot like the code that you might see in a multi-threaded programming language. Something like Java or the C++ programming language. So the idea here is to have two threads, both running the first function in parallel, asynchronously. These two lines of code here might remind you of something that we saw recently, which is the setTimeout function, right? We're passing in a function to be executed asynchronously, and we're just not passing in a timer. We're saying, hey, CPU, start this thread as soon as possible. And so what happens is when this first line of code is executed, our process creates a new thread, which also lives inside the memory for our process, and it represents a single sequence of operations. Operations like functions, and the function calls that are contained in the code of your process. This sequence of operations lives inside the call stack, which is in turn part of the thread. Like a stack of bricks, new function calls go on top of the stack, and functions that are done executing are removed from the top. So in our first thread here, we start with the first function, which is added to the top of our empty stack. And then the first function calls the second function, which gets added to the stack. And if second function made any other calls, they would be continuously added on in sequence. Now, when second function returns the value 42, the second function is removed from the top of the stack. The return value is sent back to first function, and the first function is now completed, so it's removed from the top of the stack. Now, that's if we had one thread. But remember, we're creating two threads here. So what would happen in this code is we would first create that new thread, but then we would do the same thing again. We would create a second thread with its own call stack. And these two threads would run asynchronously. So in thread 1, for example, we might go through the same flow that we saw previously. We might call first function, call second function, and so on. And then perhaps thread 2 finishes calling first function and is ready for the rest of our code for second function. Notice that the two threads don't have to be in the same place in our code, in the same state. In fact, thread 2 might even be executing a different function altogether. So it might call second function directly, or even a third unrelated function. The point is, we have processes and threads inside of them, and they share memory and code, but not call stacks. Your threads can execute side by side if you have more than one, each running part of the code of your process. And that CPU of ours can constantly switch back and forth from one thread to the other to simulate executing them in parallel. But more importantly, if we have multiple cores in our CPU, each core can be dedicated to executing one thread. This applies to all processes. Your operating system can have threads helping it run things side by side. Your code editor, like VS Code, can have threads. And even the browser you're currently watching this video on has multiple threads, helping it run smoothly. So back to our example, how does this process finish? Well, the second thread needs to complete the code that it's running. So the second function gets added to the top of the call stack. And then maybe the return value of our second function is returned back to the first function in the first thread. So it gets removed from the call stack, and that thread completes. And then the same thing happens on thread 2. The important thing to note here is that the two threads are independent of each other. In terms of executing the code, they can both be in any spot of the code depending on when they were created and how fast the operations they're executing completed. Maybe even what other threads and processes were running on your CPU. All of these things can affect which thread completes first. So threads execute side by side, allowing us to execute code asynchronously by putting it on a new thread. This sounds great, but traditionally, for your application to have threads and to take advantage of everything we've talked about in this video, the programming language that your code was written in needed to support multi-threaded programming and the creation of new threads. But the reality is that things aren't as simple as they look here. Multi-threaded programming is a difficult concept to master, especially in languages like C++ and Java, where you need to have an understanding of things like mutual exclusivity and locks. These are mechanisms to keep your code and the data inside the code synchronized between all the threads so that they can work together towards a common objective. Doing this effectively can be extremely complicated to reason about and understand, and to debug when something goes wrong. You'll run into issues like what's called a deadlock, where two threads are stuck, waiting for an action that can never actually occur. Believe it or not, avoiding deadlocks is something that experienced programmers struggle with when working with these multi-threaded programming languages. It's really not an easy job. It's a source of huge bugs in basically all multi-threaded software. And sometimes you just don't want to deal with all of this multi-threading. So that's the decision that Brandon Eich made when he created JavaScript. In JavaScript, we don't have to worry about multi-threaded programming and all those complicated concepts like deadlocks, because we can't. Traditionally, JavaScript is a single-threaded programming language. If you've already been working with JavaScript for a little while, answer me this. When's the last time you had to deal with deadlocks? Most likely, the answer to this is never. JavaScript simplifies things by only allowing one thread to execute your code at a time. So then, how is Node allowing us to open files and make HTTP requests asynchronously? Does Node introduce threads into JavaScript? Okay. Using our newfound knowledge on processes and threads, let's answer the original question. Is Node.js multi-threaded? But first, let's take a quick break. I'll see you in the next video.